Good morning, good afternoon, or good evening, guys, wherever you guys are from. Today we're going to be continuing our topics here in scientific computing. And so today we're going to continue with operation counting, and we're going to discuss a little bit more about how computational complexity works underneath the hood. So that's what we're going to be doing today. So let's start off by um, looking at matrices, specifically different types of matrices. We actually have a couple of special types of matrices. So first is we have a diagonal matrix. So that's one type. Now, what do I mean by a diagonal matrix? So let's say we have matrix A, and it goes A11, A22, A33, all the way to ANN, right? 0, 0, all the way to 0, 0, 0. So the idea of a diagonal matrix, if I pull out my highlighter, it's basically this thing, right? So that's what we call the diagonal. That's why it's called a diagonal matrix. Now let's characterize this. So actually, another notation that we can identify this with is diag, and it's basically a vector. This thing's a vector, right? That vector contains values from 0, 1, 1, 0, 2, 2, 0, 3, 3, all the way to, I keep saying 0, A, all the way to ANN, right? And let's put some characteristics. So this um, matrix A, where did I put? Let's put here. A has n by n dimensions because it has n rows and n columns. N rows and n columns, right? Okay, so that's that. We can actually modify that matrix. So now let's say, what if, let's modify this matrix to be n by m dimensions. So what's that gonna do? Well, let's say we have our matrix A, and it goes this long here, A11, then we have A22, all the way to A, that's funny, A and M, right? These are all just zeros. All of these are just zeros. These are just zeros, right? And we actually, so these are all zeros. Okay, so we actually made an n by m matrix. Actually, there's not even n. This is just something, some placeholder, and then m. This is n, right? Here we have n rows. We have m columns, right? So the way we can look at that is, well, okay. So here we have m columns. Here we also have m, and so this must mean this is n minus m. Why? Because this whole thing is n. We take out this m here, that's m. And so here we're left with n minus m. Oops. So that's the idea. Okay. And this is assuming that n is greater than m. The number of rows is greater than the number of columns. And this is also similar for n is less than m. Okay, another type of matrix that we will look at is, we call it the identity matrix. And let's denote that as the I matrix, because obviously I is identity. So I is just a diag one. Why is it a diag one? What this means, it's a diagonal matrix. So we know what a diagonal matrix is, but the values are only containing one. So an example would be identity I matrix 1, 1, 1. That's of diag 1, right? That's an identity matrix. Okay. We also have this thing we call a tridiagonal matrix. What's a tridiagonal matrix? Well, since we did I, now let's do J. Let's make it general. We have A1, A2, A3, all the way to AN, C1, C2, all the way to Cn minus 1. And then we have B1, B2, all the way to Bn minus 1. And so what do these mean? Well, this thing, the middle part, we call it the diagonal. I'll use a different highlighter. Let's use purple. This thing here, what color can we go for? I'm gonna go with this. We call that a super diagonal. I'm gonna be honest, I don't know why they call it this way. And then this last one here, probably gonna use blue, pink. I'll use blue. This thing We call that a subdiagonal. So it's basically three diagonals in a matrix. Okay, now we're going to move on and talk about computer storage. So we're going to be talking about what exactly is the concept of computer storage? What's its purpose? Why do we need to talk about it in terms of computation, right? So we're going to say that in in a computer, every number must be stored. Every number or value must be stored, right? Just like how we store integers or decimal points in matrices and vectors, right? And the idea behind it, or the purpose behind it, we're saying that it's important to know how much data needs to be stored. Why is this important? Because this uses memory in a computer. So you know how when we store photos or videos in our cell phone or when we install apps, we're consuming memory in our devices, right? And so we need to know the amount of data that's being stored since it consumes memory. Okay. So there's actually an important correlation to this. So we're going to say a lot of stored data. If we store a lot of data, then we're using a lot of memory to do that, right? And if we use a lot of memory to do that, we're saying that energy goes to it. And if energy goes to it, then it makes the computer slow, right? Either makes it slow or it even crashes because of the memory being full, right? Or we used up too much memory. So let's give an example. So let's ask how much data is stored in an m by n, oh my head, m by n matrix? That's a question. Well, we shouldn't store everything. That's the idea. Because if we store everything, the tendency is again full memory or the computer crashes, right? So even if we store like our values AMN, AM1, AM2, A2, and if we store all of those values, then the computer will get slower and slower and slower because it's using up too much memory. So the idea is we shouldn't always store everything. We can, but it makes the computer slower, right? Okay, now let's talk about this idea of data sparsity. So data sparsity in a mathematical sense is, let's say, an m by n matrix could be data sparse. If we actually Google what sparse means, I'm Googling it right now. Okay, maybe in the context of data. Keep things scattered here. So when we say data sparse, it refers to datasets where a large portion of the values are zero or null, indicating a lack of data. So that's what it means. We're missing data. Our data is not suffice, so to speak. So in a mathematical sense, it's data sparse if it is representable by, I'm just going to write it out. If it's representable by much less than mn parameters. So we're actually missing data here. That's what that means. Because we couldn't store everything in the M, M for minion, M row, and N for nice, N column. We couldn't store everything. So it means we have missing data there, right? So an example, okay, let's make it clear with an example. Um, let's say a diagonal matrix. This is an example, right? And it only stores the values in the diagonal, right? So it only stores diagonal entries. Everything else is going to be zero. So this is data sparse. So let's say if D has dimensions n by n, and let's say it's a diagonal matrix, right? So what we're actually doing is we only store n entries, not our usual n squared, right? Let's look that up. Let's say here we have some value. I'm going to say 1, 2, 3. This is what we're storing, right? Here we have n rows, and we have n columns. Actually, we have 3 rows and 3 columns, right? How many numbers did we store? 1, 2, 3. Because it's a diagonal matrix. How many numbers could we have stored if it wasn't a diagonal matrix? N squared. What's n squared? N is equal to 3. N squared is hence 9. We could have stored 1, 2, 3, 4, 5, 6, 7, 8, 9. We could have stored 9 values. But no, since it's a diagonal matrix, we only store n entries, 3 entries in our case. But in general, it's n. So that's for a diagonal matrix. Maybe we can look at a tri-diagonal matrix. Another one of our special matrix types. So a tri-diagonal matrix, how many entries can we store there? Let's see. So a tri-diagonal matrix is this thing right here. Here we store n values. We store n minus 1. We store n minus 1. And so if we add these all together, so we, I don't know how to add like this. We add these together, we have 3n minus 2. So that's the number of entries we store. Right? In a general sense, that's how many numbers we store. So a tri-diagonal matrix stores, so we have n plus n minus 1 plus n minus 1, which is 3n minus 2 entries. And lastly, now we have low rank matrices, but we're not going to talk about that right now. I'm going to look at that later in one of my exercises. Okay, so that's the idea. The number of entries that we can store in each type of matrix. And so here we're slowly getting into complexity, computational complexity. So actually, let's dive a bit into it. We're going to talk about complexity a little bit. So what is complexity? Well, we can figure out, I feel like I'm doing a caption here. We can figure out how much we need to store, right? So remember our entries a while ago. We can actually figure out how many of those we need to store based on the number of operations, right? So based on number of operations. What do I mean by operations? Adding, subtracting, multiplying, dividing. The question though is how many of those operations do we need to do? That's what computational complexity is. So the question is how many operations do we need? Let's say, I mean, in a physical sense, let's say every time we add two numbers, we're adding two numbers. If we add two numbers, depending on how big the number is, but let's say it's two small numbers, like 1 plus 1. Probably it takes a second to do it, right? Right? Usually it takes a second. And similarly, when a computer does this, also, so a computer also needs time to kind of think in a human sense, think. But underneath though, it's actually processing the values and computing it because it's a computer, so it computes. So if it needs time to think, right? So we want to determine or we want to know how many of those addition, subtraction, multiplication, and division something takes. That's how we're going to be able to determine how fast or how slow a computer program is running. So there's a thing that we do, and we count these number of operations using flops. Now, what is flops? It's floating point. So flops, FLOP point, floating point operations per second. Now, what do we mean by that? I'm gonna Google on the note. So what is flops? So it's the floating point operations per second. It's a measure of a computer's performance, specifically how many calculations involving decimal numbers it can perform in 1 second. So floating point numbers are basically decimals. So it's basically a metric for measuring computers' performance. So I guess it's a way to measure how fast a computer is, in a sense. Um, yeah, let's look at an example to learn more about how this works. Let's see. Let's do an example. So what if, let's say, we compute an inner product, right? So I want to compute an inner product. Let's say we want to compute an inner product of two vectors. So let's say we have vector v, which has n dimensions. So n rows. We have w, which is also a vector, and it also has n dimensions. So they're similar in terms of number of rows. And we say v w. Basically, we compute their inner product or their dot product. So how does that work? Well, v w. We're going to transpose v. And so that's going to be v1 all the way to vn times w1 all the way to wn. And we will get the summation all the way to n. J starts at 1, vj, wj. Now let's actually count it behind the scenes. This is in short summation, so we're going to actually expand this summation. Let's count it v1, w1, right? Plus v2, w2, plus v3, w3, we go all the way to v um, n minus 1 wn minus 1 plus v n wn. So that's that whole series, right? So we're basically counting the number of multiplications that happen and the sums that happen. That's how we're going to count their complexity. So we're saying this is 1, 2, 3. We don't have 4. Say this is n minus 1. This is n. Now, how many products have we done? This is a product, 1. This is a product, 2. This is a product. This is a product. This is a product. So we actually made n multiplications. So our products, the number of products that we did was n. That's how many times we multiplied. Let's say sums this time. So now let's look at sums. For sums, well, this is 1 addition. This is 2 additions, 3 additions. If you notice, it's after, like, you see this pattern here, we have a plus after the 1. So that's 1, then that's 2, that's 3. We do it. So this addition here is n minus 2. This addition here is n minus 1. So we actually made, for sums, n minus 1. And so from there, our total complexity, or basically the number of operations we did and when doing this inner product, is n plus n minus 1, 2n minus 1. And here we talked about big O notation. So what's the most dominant thing we can see here as this number gets big? As this number gets big, we won't really care about much of 2 and 1 anymore. So it's just going to be n. So it's actually O of n, which is linear time, which is pretty good, right? O of n is pretty good. So this is our complexity, O of n. Okay, let's try something else. Let's try computing the total complexity of a math-vec. So a math-vec is, that's for short, a matrix vector product. So we're multiplying a matrix by a vector. So matrix plus vector, math-vec. That's why it's called a math-vec. So we're trying to compute a math-vec product. Oh, actually, this whole thing is called a math-vec. Huh. So let's compute a math-vec. So here, let's say we have matrix A. We have dimensions m by n, m for minion, n for nice. And we have a vector x, which has n dimensions, n for nice, so n number of rows. And we say their product, or the math-vec, is, we'll make it general, a1 all the way to a1 of n. This is a, what am I doing? M1, and then this is AMN. And we're doing it by, okay, we have x1 all the way to xn. And from here, we will get the summation of a 1 L X L. Let's say L is the one that's moving. Here we assume it goes all the way to N, right? And here L is 1. Then we keep doing that. This is L is still 1. L is still 1 here. And here we do N, because it goes all the way to N. But now A here is M. M, L, X, L. Right? So we already derived this in the last video, but it's the dot product of this and this. That's how we get this summation. And then this last one is just this and this. Okay? Okay, so that's that. Hope you guys don't hear the plane. So what do we notice? Well, from our previous example, doing this summation here, let's say L is 1, we go all the way to N, A, J, L, X, L. Why did we call it J? Because J is just a variable. It depends. Are we on 1? Are we in 2? Are we in M? Right? J is just this thing here. I could put K, it doesn't matter. So how many operations is this summation? Well, it's going to cost 2n minus 1 operations, or that's the total complexity. Yeah. We mentioned it here, right? Doing this, that's 2n minus 1. It's the same as doing one of these. That's 2n minus 1. This is 2n minus 1, right? Now, what if we want to find the number of operations when we do this, then this, this, then this, this, then this, this, then this, right? So how many times are we doing that 2n minus 1 operations? Well, if we did it here, we're doing it 1 time. We did it here, we're doing it 2 times. We keep going. We did it here, we did it 3 times. Let's say the matrix is only 4. But if we do it all the way here, we do it m times. M as in minion. So what we're saying is, since the matrix vector product is m by 1, m for minion, because the number of rows here is m. So for that reason, m by 1, we do this summation, J, L, X, L. So we're actually doing that summation m times. So actually, if we look at it, if you look at it in a notation kind of thing, remember our A is m by n, and then our x, our vector x, is n by 1. We're actually just canceling the n here. So we're canceling this thing. So it's m by 1. Thus, m by m times 2n minus 1 total operations. That's how many times we're doing it. We're doing it n times, right? So in a big O notation, this is just O of m times n. That's the dominant thing, right? Okay. So initially it was O of n, now it's O of m times n. Now, what if, so we did a vector times vector, then we did a matrix times vector. Now, what if we do matrix times matrix? So matrix, matrix, product. Well, if we do that, let's say we let a matrix be dimensions m by n, and we let another matrix be dimensions n for minion by p. Why did I make this n? Because the number of columns of A has to be equal to the number of rows of B for this matrix to work. It's just that simple. If one of them is greater or less, then we have nothing to multiply to. Okay, now let's draw. So AB, let's make it general. A11 all the way to A1n. This one goes to AM1. Then this one goes to AMN. Fun fact, as you guys might have noticed, I switched the M and N. I actually Googled this a bit because data science does this way. M is actually the number of data points, the number of observations. So data points are observations in a data set, and N is actually the features. So that's just notation in a data science perspective. Features, I mean, let's say you have a data table, right? Features, I mean, like, let's say name, age, height, I don't know. And then your data points could be like Josh, age could be like 40, height could be like 6 foot, right? So here we're talking about features here. These are features or columns. While these are not that. Specifically this one. Here we're talking about rows. So these are data points. So that's just the idea, but I don't think we'll get into it in this scientific computing. Yeah, we're mainly focusing on the technical side. Anyway, so let's continue. B11 all the way to B 1P. This is all the way to B N. N as in nice. And 1 all the way to B NP. Right? Okay. Now we want to count the complexity here. Let's see. Remember when we did a matvec? A matvec operation is n times 2n minus 1. Where was it? I lost it. Oh, there. M times 2n minus 1, right? The thing I just showed you where we did this piece here. So we did this and this, this and this, this and this, this and this. Okay? the number of multiplications and addition that happened there was m times 2 and minus 1. Now, if we do a matrix product, here's what we're doing. We're doing this, then this, similar, right? Then this, then this, then this, then this, then this, then this, right? So that's how many times? M times 2 and minus 1 times. What's next? Now we're moving on to this column. We do it again. So this times that, this times this, this times this times this. How many times did we do that? We did that twice now, right? So what I just said is, remember, we one matvec operation is m times 2 and minus 1. And now if I did it the second time, I'm just multiplying everything by 2. So I'm just multiplying 2. And if I keep doing it again, now I go to, let's say, my third one. We did this times that, this times that, this times that, and this times that. How many times is that now? That's 3. And let's say we do it all the way until we reach B. So this times that, then this times that, and this times that, then this times that. So that's how many times now? Not 1, not 2, not 3, not 4, P times. Right? So what I'm saying is, one matvec, so we call it a matvec, right? A matrix vector product. Oops, handwriting's ugly. So we're saying one matvec has m2 and minus 1 operations. One matvec. But here, how many matvecs do we have? We have p matvecs. So doing this computation complexity p times, I think we can understand p times, gives us total of p m 2n minus 1. So that's now our total number of operations. Okay. So we say in big O notation, we say this is O of P M N. Now, what if, let's try this. Let's say, to put this into perspective, or to make it even more general, say P, M, and N are equal. So a matrix by matrix multiplication will be O of n times n times n. N times n times n is O of n cubed complexity. So that's really bad in terms of efficiency, right? If we actually look back in our previous discussion, and we look at the graph, right? Ooh, so it's not there. Okay, I guess I didn't. Big O notation of everything, basically. Uh, is there an n cube here? cube maybe. Oh, there we go. We have a nice one here. Or is this good? Actually, we can just use this. Yes, I'm gonna use that. And boy, would you look at that. Oh, wait. Yeah. Oh, shoot. My thing's not working again. Okay, that's not nice. Okay. So here we can see that O of n cubed, as it keeps on increasing, will definitely be greater than n squared. And so if it becomes greater, then the time is worse, right? So actually here, another thing that I forgot to mention is here, say m is equal to n, then we have O of n squared. So we're trying to make it as general as possible, assuming they have the same number of rows and columns, right? So we're just assuming. So this one would take O of n squared. If it has a different number of columns, let's say m is greater for minion, m is greater than n for nice, then it's probably worse than O of n squared. But this is a good estimate of how fast our program is going to run. So ideally, constant time O of 1 or O log n is good. Both are really good. But when we get to, let's say, O of n cubed, then that's just worse. Or even get to like, uh, I'm pretty sure there are like other ones, like uh, O of n factorial, O of 2 to the power of n. Yeah, those are really, really slow, basically. They take a lot of time for the program to run. Wow. So yeah, okay, let's make our n more concrete. So let's say, let's look at this. Let's say n is 10 cubed. What's 10 cubed? 10, 1, 2, 3, 10,000. Let's say n has 10,000 rows and columns of data. So what would the complexity be? The complexity would then be, so if this were n, I think it was n cubed, right? N cubed, we plug in this for n, we get 10 to the power of 9. 10 to the power of 9 is definitely a big number. So what does that mean in our context? That's a lot of operations. That's a lot of addition and multiplication, right? That's a lot. Let's say if we do n equals 10 to the fourth, right? Complexity would be, so you're just doing some basic uh, multiplication. 10 to the fourth, if we do O n cubed, then that would be 10 to the 12, which is like 1,000 times more. So that's a lot more addition and multiplication happening in the when the computer's quote unquote thinking or processing the data. And we're gonna admit that 10 to the fourth for an n is not unrealistic since we have a lot of data coming in. So that's definitely not unrealistic. That's realistic. And so what happens is that computers in practice use better algorithms with lower complexity. So ideally, computers in the real world, they use better algorithms in order to lower their time complexity, right? Let's see. Um, mm, 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 mm. Yeah. By doing things, but yeah, that's the idea. By doing things smarter, it gets a lot faster. That's basically the idea. So we're gonna say, actually, I'm not gonna type. I'm not gonna write that. That's self-explanatory. Okay, so now let's try it in some cases where we can maybe lower our time complexity to make our programs more efficient. So let's say we can also do better in specific cases, right? So let's say, for instance, we have matrices that are data sparse. So we already unlocked the term data sparse, missing data. So for instance, we have data sparse matrices. What's an example? Well, from one of our special matrix types, a diagonal matrix, right? So let's say D is a diagonal matrix. Oops, my A looked like a D there. It's a diagonal matrix. So let's look at that. So let's characterize our D. Our D has dimensions n by n. So it has n rows and n columns. So it's basically a perfect square. Then let's multiply it by a vector. Let's say vector x, which has dimensions n or n by 1. So let's just do n. And so what do we have as a result? We have dx. Here we just do summations, right? Actually, we don't even do summations. Let's say a11, a22, I believe. I don't even know. It's just a bunch of values. What does the diagonal matrix look like again? Like at least in general. Oh, there we go. A11, A22, A33, all the way to A and N. So A11. Let's keep it short actually. Let's probably do it like here. A11, 1, 2, 3, A and N. That's it. All of the rest is 0. We're multiplying it to x1, 1, 2, 3, all the way to xn. So what is this going to be? Well, if we actually do our math-vec multiplication, we're going to multiply x11 to here, and the rest is just going to be 0. So 0 times x2, 0 times x3, 0 times x4, all the way to 0 times xn. So we're going to store a11, x1. And now we're going to continue. Now we have a2, 2, x2, right? And we keep going until we have a n n x n. And here we can actually count the complexity of this thing, which is surprisingly how many additions and multiplications do we do here? Well, look how many we have. We only have n products. And since we only have n products here, our complexity is O of n, constant time. Right? Sure, we add n times, right? We have a1 1 x1 plus 0 0 0. 0 doesn't matter. We don't store anything. We're multiplying n times. That's it. We're not even, I don't want to say we're not adding anything, but technically we're not. We're adding with 0, but 0 is nothing, so it doesn't count. It's useless. So technically we're multiplying n products, but we're not adding anything. So complexity here is O of n. Now previously we did the same thing. We did a madvec. But if you look at this is O of n squared. So this is slower than a diagonal matrix multiplied by a vector. Obviously, I mean realistically, because you're multiplying and you're adding every single value in the matrix A. But here you're only multiplying the values that are diagonal, right? Because it's a bunch of zeros, so it obviously takes less time to do that. Or for the computer to think. So if we use a diagonal matrix instead of a regular matrix, then it's O of n instead of our previous thing that we got, which was O of n squared, right? So yeah, I mean, that was all for the lecture, I think, or I could give more. I could probably talk about, let's see, probably have something else on my list here that I wanted to talk about. But yeah, I mean, that's the idea of computational complexity. Oh no, that's it. Okay. That's the idea of computational complexity. Um, yeah, just write code that's more efficient, basically. Um, yeah, I mean, that's pretty much it. Yeah. Next time we're going to be talking about this is going to be something interesting. So next time, I'm actually going to look at my stuff here. I forgot. Um, okay, next time we're going to be talking about systems of equations. Think of systems of equations. I might do a little bit of coding, maybe, but we're gonna see. We're gonna see. Um, yeah. So next time we're gonna be talking about yeah. For scientific computing, I'm only gonna do the math stuff because that's what usually gives me the trouble. Um, yeah. Next time we're gonna be talking about systems of equations. I'm just gonna type it out. Systems of equations. So this idea of AX equals B and Gaussian elimination. And we're going to apply what we learned from vectors and matrices in order to do that. Oh yeah, I forgot. It's gonna be week 2. So yeah, just a little bit of a teaser. I'm gonna switch this here and delete this. Yeah, next time we're gonna be talking about systems of equations, and then maybe a little bit of iterative methods for this idea of ax equals b. And then more on direct and iterative methods for the next one. The difference between those two. Do I do and or just do versus? Yeah, which one's more faster? Which one's slower? Probably, I think that's what it wants me to do. But yeah, okay, I'm gonna stop here and I'll see you guys in the next one.